All right, let's get started. Welcome everyone to the Ready Set Roman Training Series number 6. My name is Ori Fox. I am the SOC Deputy Project Scientist at the Space Telescope Science Institute. This is a training series that's put on in collaboration with both Space Telescope and IPAC. And if this is your first time joining us, as a reminder, we have had a few webinars already um, on various tools as we start preparing for Cycle 1 call for proposals and Cycle 1 data. If you've missed any of these, we have recorded everything and they are available online at both our outer space page and also on our YouTube channel. You can find that QR code here. If you have not already done so, be sure to subscribe to our mailing list. That's how you can keep up to date with all future webinars and calendar invites. And speaking of which, I'm happy to announce that we have a few more webinars planned as we lead into the Cycle 1 call for proposal due date, which is March 17th. Today, we will be talking about data analysis specifically on the Nexus. But next, in a couple weeks, on January 27th, we'll actually be, on February 10th, we'll be doing more of a deep dive on the Nexus. That's going to be training webinar number 8. On the 7th, for the webinar number 7 on January 27th, we are going to provide a mini workshop on preparing for Roman. This will include aspects of the workshop that was held recently at the AAS in Phoenix. For webinar number 9, we are still defining what that topic will be. And on the March 10th, we will review some of the top help desk questions that we've received and provide more of an interactive sort of hour to address some of these questions and to answer other questions as we lead into that final week before the proposal due. Speaking of which, this is a reminder that the Cycle 1 call for proposals is out and due March 17th. You can find that all at the QR code here or at the links. Again, these slides will be shared later this week, so you can go and click for yourself. There are a number of different proposal categories, including analyzing existing Roman WFI data that will be obtained through community-defined surveys. We've had a couple tutorials on that already on how to explore these surveys and see what sort of data will be provided. You will also be able to propose for new general astrophysics survey observations, as well as theoretical and laboratory astrophysics research, not to mention ancillary data that might be relevant to the Roman mission. That takes us to today's topic. Roman is going to be a big data mission. It will produce over 20 petabytes of data in 5 years compared to Hubble, which produced 172 terabytes in 30 years. That means it is going to be hard for you to take the data and download it to your own personal machines. Not impossible, but very difficult. Instead, it is our goal to bring you to the data. And we do that through the Roman Research Nexus. We are going to dive into that today. It was just launched for the new year. We made a big splash at AAS last week. We sent around instructions prior to this webinar on how to log in and start exploring the Nexus. If you haven't had a chance to do so, again, here's the QR code and the link. The Roman Research Nexus is a science ecosystem that will provide cloud-based computing for the science community to explore, access, and analyze Roman's petabyte scale data. Not only will you be able to do that, but we are providing a precompiled research environment that includes software, algorithms, and tutorials for you to learn how to work with the Roman data and do your analysis. It's completely free, no registration is required. So that sort of sets the tone for today's topic. With that, I'm going to hand it over to Javier Sanchez, who's going to be leading today's webinar. Javier, I'm going to turn it over to you right now.
Thanks, sorry. So I'm gonna go share my screen and let's go to present mode. Can you see my screen? All right. So thank you and welcome to the webinar. As Ari said, today we are gonna discuss a first pass workflow on the Roman Research Nexus. Early February, there will be a more in-depth presentation about the Nexus itself. So I'm gonna be focusing more on the usage and not as much on like the technical aspects of the Nexus today. The goals are gonna be first how to log into the Nexus. The second part, I'm gonna describe data analysis workflow. So what would be the typical way that you would interact with the data? In principle, as Ori mentioned, right now we are in a new era where there's a lot of data and it's hard to use the typical mechanism of downloading all the data into your laptop or local machine and start the analysis. And we need to shift to the paradigm of like going to the data or where the data is and analyze it there. And then I'm gonna show an example analysis and go a little bit over the workflow. I'm also showing here a QR code that Ori did for like to log into the Nexus, and there's the URL. And basically, once you log in, you see, so once you go to that URL, the website that you see will be this screen right here. If you have an MyST account, you can click on the bottom and just open it. Or if you are a new ST user, you can create your new account and then you will go into the next page. So you either click on one of those and then something like this will pop up. You have many modalities or servers that you can choose. In principle, today I'm gonna focus into a set of notebooks that are available on the Nexus, and they should be all run. Like you should be able to run them using the personal server. Depending on the type of analysis that you make, you might require a different server, but also depending on the type of server that you choose, you will be charged a different amount of like credits. And that's gonna be discussed more in depth in the next presentation about the Nexus itself. So in principle, the notebooks and analysis that I'm gonna describe are gonna be doable using a small server. You can choose the medium server for a bigger job. The difference mainly is that one has 2 virtual CPUs and 64 gigs of RAM, and the other has 8 virtual CPUs and 64 gigs of RAM. When you choose the server, you can also choose the image of the software, so the environment, let's say, that you're running. In this case, I'm using the latest version of our software environment, but you can use different versions, just clicking there. And then once you choose your own, once you make your own selections, you can go to the bottom of the page and you will see this button that says start server right there. And then you click on that and it will load. Then you will get like a loading bar, and it will take a little bit of time depending on the amount of users that are connected at that time. So it can take up to 15 minutes. Don't panic if it takes a while, especially when you allocate larger servers. It typically takes longer, but in principle, it should load and it should work. And if you find any problems, you can always submit a ticket to the help desk, and we'll try to fix it as soon as possible. So let's say that everything loaded correctly. You will see a page like this. This is the landing page of the Nexus once you have it up. So the Nexus is basically a Jupyter lab instance on the Amazon Web Services. The first thing that will pop up is an intro page, and in that intro page you can choose what do you want to do next. It has a little getting started here. So how to work with Jupyter Lab, how to manage your server, and more information about this. The Roman science workflows, which will be the topic that we will be discussing today. Then notebook tutorials, the available data on the notebooks themselves, information on how to work on teams. So one of the nice capacities of the Nexus is that it allows you to interact in teams, and you can share data, you can share software with your team. And then information about how to monitor credit usage, installing extra software, and about and a link to the documentation itself. So as I said, today we are going to be focusing on a typical analysis workflow. So the idea is that once you log into the Nexus, the first thing that you would do in your analysis is like, okay, so where's my data? So we have a notebook that is called the data analysis and the data discovery and access notebook that explains this particular aspect. And it tells you how to retrieve the data from the cloud, either from an open data bucket in S3 or from the open data buckets where we have simulated Roman data, or using the masked Astro query itself. Then once you know what data you want to analyze, the next step will be opening that data. And in this particular case, Roman data is going to be distributed in this format called the Advanced Scientific Data Format, which is also pronounced as ASDF. And there is a notebook there that tells you how to open ASDF and the information about particular aspects of ASDF. And like you can go in depth into that notebook and explore more about the format and how to interact with it via Python. And then the next thing that you would typically do in your workflow is, okay, open, for example, images, go over them, see if there is like anything, a defect or something unexpected on the images. So do a visual inspection of the data. And in order to do that, there is also an example notebook that is the data visualization notebook that tells you how to basically open these data, visualize them using a variety of libraries. For example, either Matplotlib or using an interactive tool called JDAvis. Last but not least, so what you would do is analyze their data and perform your analysis. There is a set of notebooks with different example analysis here. So there is the one that we will be talking more about today is the aperture photometry analysis, where we will use simulated Roman data and perform forced aperture photometry. But there is also one that is about how to measure galaxy shapes using Gaussian HSM code, how to generate cutouts of Roman images, for example, for machine learning analysis, how to do Grism spectral extraction, so how to use the Grism images and do like an spectral extraction, and how to even analyze data from the thermal vacuum integration testing campaign from a test called the Bright Star test, where like point source was illuminating a particular sensor in the focal plane of WFI, and that is real data from the telescope. Well, not from the telescope, but from the camera. And so once you are in the notebook and the Nexus, sorry, you can click on the analysis workflow, and it will open this page. As I said, it describes the workflows themselves and the different notebooks in the workflow. So as I said, there's the data discovery and access, working with ASDF, and then the different analysis notebooks. So I'm gonna switch gears and move to share my Chrome screen and the Nexus itself, so you see these in real time. All right. Hopefully you can see now the screen. So as I said, when you log into the Nexus, you will land into this intro page. You click on your Roman science workflows right here. and go to the workflows page. And in this case, we are interested in the Davify data analysis workflow. So we click on the Davify data analysis workflow, and it puts us into this markdown document that has documentation on how to go over these analysis. You can have any of these links direct to the particular notebooks. And in this case, what I'm gonna focus on today is the aperture photometry notebook. The reason is that this will explore a little bit of all the aspects of the previous basic steps. There is more in-depth information in each one of these, and you can go on them. Yeah, or
I just wanted to mention, I forgot when I was giving my introduction, but if you would like, and it's encouraged, I posted the link in the chat. You can all try to log in and actually follow this in real time. There's no compilation required. You can just open this notebook and run it. And of course, we encourage questions. We don't want too many questions throughout the presentation, but we also want you to be able to follow along in real time. So if you do get stuck or have any problems, feel free to raise your hand and we can try to answer them. If you can keep your question until the end or post it in the chat, feel free to do that and we'll get to the question at the end or try to answer it in the chat in real time.
thanks, Ari. All right, so as I said, I'm gonna go into the aperture photometry notebook. So you will click here. In this case, I have it open already, so I'm gonna just move to it. So we have this notebook that is gonna explain us how to do aperture photometry on the Nexus. The first thing that it tells you is like select and make sure to select the Roman Research Nexus kernel. So if you're not familiar with Jupyter Lab, this is the overall interface. Jupyter can execute Jupyter, Julia, Python, and other languages. In this case, for most of our notebooks, or all of them currently are in Python, and most of the software of the Science Operations Center is in Python. So this is Python centric, but of course you can use your own code in other languages in this environment as well. In principle, make sure to use the Roman Research Nexus kernel. So you will go here onto the top right corner, click and select the appropriate kernel. So you click on this caret and then go to Roman Research Nexus and select the kernel. Since I had it already running, I don't need to switch it. This kernel contains all the environment already and the pre-requirement packages pre-installed. So in this case, you need AstroPy, a regular library for astronomical analysis, NumPy, the copy library, which is also basic from Python, Matplotlib to do the plotting, FogUtils, which is an AstroPy affiliated to perform photometry measurements, Roman data models, which is the package that basically tells ASDF, which is the library that manages the data format, how to open Roman WFI data and how to handle the data model itself, the ASDF library to open the WFI data as well. And then we have the S3FS, which streams the data from the cloud from S3 buckets in AWS, and STPSF to do like the aperture correction. Basically, we're going to use it for that. So the typical notebook workflow, you have your boilerplate cell with all of the packages that you're going to use and import them. So we import all these packages, AstroPy table to read the catalog that we will be reading, AstroPy stats to perform Sigma clipping statistic analysis, ASDF to open ASDF files, and CRDS to retrieve data from the calibration reference data system, and then FOTUtils to open to perform the force photometry measurements themselves, Roman data models to handle the raw data, and S3FS to access the data on the cloud themselves. And STPSF, as I said, is to compute the aperture photometry, the aperture correction. So here we have an introduction of the notebook and the goals. You can go over these on your own leisure time. Basically, the idea here is like use simulated data and perform a force photometry analysis. So the first thing that we do is open an image, and in this case, it's a level 2 image, which means that this has been calibrated. It's a ramp. So basically, the units will be DNs per second, and it's already corrected for all detector effects, so saturation, nonlinearity, etc. So basically, here it shows how to do this. So if we have already the data downloaded, what it does is it calls Roman data models and opens it. If not, in here, what it does is we go to the S3 file system and go as anonymous. You don't need authentication for this particular data. We have the location of the data here. This is where all our simulated tutorial data is going to be. And then we know that we are going to deal with this image, with this calibrated image for a particular sensor, W501, in a particular band, F106. And then we tell it to open it. So we use Roman data models, pass the URI, and open it. So we open the data from the S3 bucket with this command, and then we identify the different data blocks. So this data is in ASDF. It has different data blocks. The data, the main science images is going to be in the data block called data. So we access it using this dot syntax. So f.data contains the image, f.error contains the error image, DQ contains the data quality image itself. The metadata is containing this meta block. So we make a view of this meta block here in meta, and then the WCS, which is a generalized Python WCS object, is contained in this meta.wcs data block. So we get all of these going and have them handy for the next steps. The next step is gonna be so we are gonna perform force photometry. So we are gonna use the known position of the sources, because this is a simulation, we know where the sources were. So we use the catalog here and open it, and we use the positions on the catalog, on the truth catalog, and perform the force photometry in those positions. So in order to do that, what we're going to do is stream that data. If we have downloaded the data again, we open it using AstroPy table, because this is an CSV file. Or if it's not downloaded, we stream it and open it. So you use the file system, open it as a byte stream, and then once you have the byte stream, you tell AstroPy to read it and the particular format. So first you will run these cells, and the way you will run them is you click play button, or you go to each cell and do shift and return, and it will run them, and you will run all these cells, and then once you are ready and run these cells, you have access to the catalog. So in this case, I'm gonna print the first 5 rows of the catalog, and these are shown here. So you have the right ascension, the declination, type of source, either a CERSIC source or a PSF source. So we use CERSIC profiles to describe the galaxies in this simulation, and PSF like for point sources. CERSIC index, the half-life radius, position angle, axis ratio, and then these columns are the fluxes in Magis of the source in the different bands. So what we are going to do next is, in order to perform the first photometry, we need to do it in the detector coordinates. So we use the WCS and the array and deg of the truth catalog, and get the positions in the detector coordinates. So we use this command where we invert the WCS and go from sky coordinates to detector coordinates, and pass the array and deg in degrees, and obtain the XY positions. And then you can also check the number of galaxies and sources that you have, and count them. And for example, here you want sources that are on the detector, so where the X and Y are finite, and where also you want to see whether they're a star or a galaxy. So it's a star and it's on the detector, so it's in the detector and it's a PSF type, or it's a galaxy if it's in the detector and it's a Surshek type. So we run these, and we have 1,700 sources in the detector, of which 1,500 are stars and 145 are galaxies. The next thing that we want to do is to basically get their AB magnitude, and in order to do that, we run this command. So basically we convert from Maggie's to AB by just doing the -2.5 log 10 of the fluxing Maggie's, and then we make a histogram of these sources. So this is the magnitude distribution of the galaxies, and this is the magnitude distribution stars. In this case, these are simulated. I don't remember if they are realistic or not. I'll now go back on the question later. And then in order to make the force photometry measurement, we need to correct for geometric distortion. So we are gonna query CRDS to get the pixel area map. So we do this by doing this command, running this command. So we get the reference. In particular, the reference that we want is the area, and we are gonna query the area for the particular detector that we are using, which is WFI1, for the particular exposure, for the particular time at which the exposure was taken. So we run that and obtain the CRDS result, which is basically this area map that has been stored in my cache. So now I go here, and using Roman data models, it understands the type of data. So I tell it to open this area reference file. So I get it here, and then I show it. And this is basically the area, the pixel area map for the WFI1. So in order to correct the data for these changes in area due to the distortion or the relative sizes of the pixels in the sky, I multiply the image itself by the pixel area map and the errors as well, and that will take care of that correction. Then the next step is to generate the circles or the apertures in which to measure the aperture photometry. So we are gonna do a 3-pixel radius. We will use the truth positions and just throw the apertures there. And then we'll measure the background using circular annuli with an inner radius of 20 and an outer radius 25. And this is to basically subtract the background then later. Here in this notebook, we also show how to create a quick visualization. You can explore more about how to visualize this data using the data visualization notebook. But here we just use PL matplotlib imshow. So basically, we just imshow the image. The image itself is going to be a plain NumPy array. So you can just show it like this. And then we plot the circles with the apertures and the background itself. So we have this like a small solid aperture where you're going to measure the flux for the stars, and then these like dotted rings here or tori are going to be where you measure the background. So we have these point sources, and we'll measure these fluxes, and then here is the photometry. So you basically run these aperture stats and on the image with the apertures that we defined and the error image, and passing the error image that we defined at the beginning, and that generates a table that we can export. So we have these measurements and we dump them into a table with the columns here that we define here. So the ID, the centroid, the tau, sum within the aperture, and its error. And this is what the table looks like. So we have different stars, and these are the center position, the tau flux, and their error. We also repeat the same for the background apertures, and this to then subtract the background flux, and repeat the same procedure and get the flux in those background. And then we are gonna convert that into like physical units. These sum and sum error are just in counts. So we are gonna convert into physical units, and in order to do that, we use a 0 point. So we convert from dns to megajanskis per steradian, and so what we have to do is basically so first we subtract the tau flux in the ends. We subtract the background times the aperture size, and then we convert that to Janskis by multiplying by the 0 point and the pixel area itself here. So after that, we do a quick aperture correction. So we use the PSF on the center of the detector here, calculate the PSF and check what is the encircle energy at different radii. And we have this graph here that tells us what is the encircle energy given the different radii. So after that, we get the encircle energy correction as 1 over that times the pixel size and the radius that we chose. We chose 3 pixels, and we get the circle, the aperture correction to be above 1.22 for the radius that we chose. And then we compare to the input photometry by converting the flux to AV mags, and then here in this we just will show a scatter plot of truth of input minus measure as a function of the input. So here we have the measurement, and as you go fainter, the scatter increases. There is some offset due to several approximations that we did here. So we are using an aperture photometry and using the PSF on the center, and we are using the average pixel area. So basically, there is a few approximations there that we made that don't make it perfect, but it's very close. So this is basically the whole analysis. You can go over the notebook on your own leisure and at your own pace. If you have any comments or questions about it, we are happy to take them either via a help desk ticket, or you can also create issues in the repository. And that is all that I wanted to show today. I'm happy to take any questions.
Thank you, Javier. That was excellent. You did get a few good questions in the chat. We can go over those in just a second. And I just want to reiterate what Javier said in the beginning, that this is one notebook in a larger tutorial workflow about how to analyze Roman data. But this is not the only way to analyze Roman data. Um, you are able to bring all of your favorite tools, software, algorithms to the Nexus. Um, you're able to upload them and run them. So this is just one example. That's the nice thing. You have the flexibility to work with the data in any way that you want to, but this gives you some insight about some of the particulars in terms of dealing with ASDF files or dealing with the conversion from DNs to magnitudes and things like that. So this just starts to give you a sense of how to work with the data. All right, so let's go to the questions. I'm just going to read them in order. The first question was, is there any cross-validation procedure with existing public release catalogs of known object positions, such as SDSS?
In this notebook, no. I mean, this is a simulated image. I don't remember the origin. I think this is just a mock, and I don't think that the magnitude distribution is realistic. In principle, for an analysis, you could potentially use the Nexus and query whichever service with the known object positions like you would like. So, for example, you could potentially create, if it's queryable, you can use the API to query the flux of SDSS sources in your notebook and check there. But in this notebook in particular, there's not.
Yeah, and I don't know if Charles wants to comment or anyone else online. I can write this down and we can get you a more technical answer, but I don't want to be quoted on this, but I also want to try to give you some information. From previous conversations, my understanding is that we are not going to provide a joint catalog or cross-match catalog. However, there are, as Javier was hinting at, there are Python algorithms such as, nearest neighbor or something like that, where if you just have the two catalogs, you'll be able to do the cross match very easily yourself. That said, as we develop things and go forward, I think we do recognize that this is going to be a very common task that people want. And at least it's on my radar. I wouldn't be surprised if there are notebooks that get developed in the future that sort of illustrate how to do this for the average user who might not even be familiar about how to use nearest neighbor. Does that answer your question, Majidin? All right. Next question. How do you deal with source confusion? Joint PSF fits for multiple sources.
So in this case, because I'm doing force aperture photometry, I have the true input position of the sources. So I don't have to do any, like there's no confusion because I have the real truth. In real data, what I think the Roman Cal pipeline is supposed to do is a joint fit, but I don't remember the specific, and I'm not sure 100% of the specific details of the algorithm to be used.
Yeah, and if anyone wants to, I'm writing these down so we can get these into the documentation in the future. Again, I don't want to be quoted on any of these answers, but just to add to some of that, I believe the catalogs will be PSF photometry. In crowded fields, you're always going to have a problem, no matter what telescope you're using. And so this sort of goes back to how I began this conversation, which is if you have your favorite PSF photometry tools, you can bring those to the Nexus and analyze specific fields where you might expect some source confusion, if that's something that you're thinking about. Alternatively, I do want to point out, and maybe I'll put a link in here after we get to the next question. There are what we call WFS, Wide Field Science funded programs through the Rose's call in NASA to develop deliverables for the community that hopefully the community will make use of. And one of those, or at least maybe even two of those funded programs, is to develop crowded field PSF photometry tools that may work better than your PhotoUtils PSF, for example. So stay tuned. There's probably going to be more development on that in the future. Just keep up to date with the documentation and the notebooks that come out on the Nexus. All right, Ilaria, Daniel, does that answer your question enough for now?
Yes.
Okay. The next question, which are the units for the sum and sum error? I think you addressed this, but maybe you can say it out loud one more time.
Yeah, so in that case, because the image itself was in dns per second, I was just doing the sum within the image, so it was in dns per second, and then we did the conversion to physical units.
Great. Next question, do you expect to limit the number of Nexus users at a certain point? For example, if this does not respond well.
I am not sure. Do you know that in this one, Ori?
My understanding is that is not the plan. Again, I want to start every question with I don't want to be quoted. We don't expect that to happen. Part of the throttling, I don't like nobody likes that word, but there are these credit systems to limit how much people will be able to use the Nexus. I want to be careful about the way I phrase this. The Nexus is an online platform, but is not necessarily a high performance computing center. So the goal is not for people to necessarily make this their big data machine learning computer cluster, for their personal use. It's to bring them close to the data to perform. It might be large scale analysis, but maybe not high performance computing. So there are limits and checks in place. We don't expect it to get to that point, but if something changes, there will certainly be an announcement that's specific to that. All right, next question. Please elaborate more on the uniqueness of any Nexus data model.
I think so. The Nexus has a similar spirit to other what would be called science platforms. So, for example, Rubin has a science platform. I think that one of the things that is unique to the Nexus is the ability to share software and data among teams, and the ability to create teams. I'm not sure if that's the case now in Rubin, but it didn't used to be. So I think that's one of the key aspects. Technically, they're very similar. I mean, one is a Jupyter instance on AWS. I think the other is like based in a different service, but yeah, it's not 100% unique in a sense, but it does have some unique capabilities. Yeah. Anything that to add, either Shah or Ori?
No, I do not. All right, next question. How about the application of the source detection in a cutout image for fast simulations? Is it easy to get photometry uncertainty of individual sources and an incompleteness map?
Yeah, so photoutils has a detection algorithm that you can use in the cutout image, and it will do detection segmentation, and then you can compare to the input and get the incompleteness. I don't have the particular example here, but it might be a good idea to include.
All right. Any other questions? While you ponder that or have another question, I do have a question for everyone here. If you're willing to volunteer, I'd like to see a show of hands of who actually logged in and was able to follow along in real time. If you you know, there's no grade, there's no prize, there's no punishment. All right, we got some people. Excellent. Great. All right. There you go. Wow. Pretty good. I'm thrilled to see that. Thank you, everyone, for doing that. That's a good start. Does anyone have any feedback about the use of the Nexus that they'd like to share? Things that worked well or didn't work well? If you've used other platforms, as Javier mentioned, there is the Rubin platform. One thing you will advertise when we do our deep dive on the Nexus is one of the big advantages that we're touting is the fact that you're able to do collaborations. In other words, work on teams where you have joint accounts, and you're able to work together in real time, like a Google Doc on a Jupyter notebook or code or something like that, which is, you know, really is going to be really nice for collaborations on this work in the future. But yeah, any feedback? I don't know if Daniel, if that's a hand that you've kept raised, or if you want to, or if you have a comment you want. Okay, that went down. Every step worked well. Thank you. All right, here's a comment. What I really like on the Rubin Science platform is that the tutorials are available at all times from a bar pinned at the top of the thing. Uh, yeah, so I don't know if you want to talk to that, Javier. I mean, we can go back to the screen. All tutorials are sort of available at all times. I mean, I could make the argument that that's the case here. Maybe you want to show that.
Yeah, so the tutorials here are also available at all times. So every time you log in, it will pop up open this intro page, and you can go to the notebook tutorials at any time, and it shows all the notebooks here. So in that sense, it's similar.
All right, and Katarzyna, I see your hand is raised too. Do you want to follow up on that? Go ahead.
Yes, so I
Oh.
really like that. Sorry, that I was writing the comment. I really like that the tutorials are already here when you log in. But when I was like developing my own, you know, crazy code that's made of 4 tutorials, I found it very helpful. Like there was a little bar at this Ruby Science platform. There's a little bar at the top, and you can click at the tutorials, and they're like split into categories as in here. And I think that might be useful too for users, especially if they want to do their own custom code and they need to pull quickly from like 5 tutorials.
Yeah, I'll go. I don't know if anyone's on our team can comment from the room. I've used it a little bit. I must admit, not as much as maybe I should, but we can certainly. I'm making a note of that, and we can at least look into that aspect for the user-friendly approach. So thank you. That's good feedback. Let's see. Another question came in. Where can I find a list of people, my students, or I can ask for technical questions? Great point. I'm going to include that link in just a second, as well as the link to the awarded programs. I just forgot about that. The best place to go is our help desk. We have a very comprehensive and efficient help desk in place. It uses the same technology and implementation strategies as Hubble and Web. So we have that down pat, and that's definitely the best way because it allows us to keep track of all questions and make sure that your question gets routed to the right person. So I'm going to post that in just 1 second. Let's see. All right, it is posted. All right, any other questions? And while people are thinking, Charles or Carrie, Is there anything that we missed or overlooked today that should have been said that wasn't said?
Hey, Ori, this is Charles. I just want to reiterate that while Nexus is public and accessible to all of you, it is still in development. We're still actively working on adding notebooks to it, tutorials, but also the underlying infrastructure, and maybe to some extent also the presentation of the Nexus. So keep using it, log in regularly, and you may see that things evolve with time and get better. And all the feedback that you are providing is very useful to us, and we do our best to improve the platform based on the feedback that we receive.
And there was a question about whether there will be more in the future seminars. And yes, I'm not sure if you logged in a couple minutes late or not, but in the beginning, I posted the upcoming schedule. We have not updated the website yet. This is all just brand new, a brand new schedule that came out. Great. And Leslie posted the link. We're going to update that schedule in the next couple days. But we're going to have a few more webinars before the call for proposals, cycle 1 proposals are due. I can share my screen again, I guess. Let me do that real quickly to address this particular question. I can find it. One second, and maybe that's a good way to end this with one last advertisement for the upcoming schedule. So this is not going to be the last time we talk about the Nexus. We're going to do so again on February 10th. That will be more of an overview combined with a deeper dive on really how to get around in the Nexus and understand what the Nexus's capabilities are. We're also going to have a mini workshop on January 27th, which is sort of taking the material from one of the splinter sessions at the AAS on how to best prepare for Roman, including cycle 1 and the call for proposals. So we'll kind of go through a comprehensive overview of all the different tools and resources at your disposal. And then as we get into March, we'll really start focusing on the feedback from the community, specifically what sort of help desk questions we're receiving, and we'll try to address some of those big questions. Because they say for every one question, there's 10 other people thinking it. So we want to make sure the whole community knows all the answers. All right. Anything else? Oh, one more. Here we go. Do we have to subscribe individually or separately? Great question. You do not have to subscribe at all. You can just join. I'm going to share on the website that Leslie posted, actually. There are instructions on how to sign up for our mailing list. I recommend that as the best way to stay up to date about which webinars are coming up, how to log in. It's going to be the same link every time, but at least it provides that reminder. There are other options. You can follow us on social media if you aren't already. We're on Instagram, Facebook, Twitter, Blue Sky. We post announcements, reminders the day before. I'm going to put our handle here. And we also have a blog that we send out weekly, and I'm going to put that link as well. There's so many ways to get involved where you can sign up. Which is right here. But the short answer is no, you don't need to do anything. You just need to be aware of when it's happening and sign in. So That takes us right to the end of the hour. That was great. We had lots of time for good questions. I want to thank Javier so much for that great presentation. Perfect length, perfect amount of detail. And I really hope everyone starts using the Nexus, getting familiar with the simulated data sets, and writes a great Cycle 1 proposal. All right. We'll see you in a couple weeks. Oh, one last question. Oh, no more last question. Okay. Bye-bye, everyone.